All right, welcome to Chapter 4, Section 6, called Regression and Medium Fit Lines. This is for IM1 or Integrated Math 1. So just as always, I'm going to go over the first screen here just so that we look at the features. You will see a due date on your student screen. I don't see one on the teacher preview, but you'll get one right here before attempts. And the attempts here, it's showing me that I'm on attempt number 1 of unlimited attempts. This means that I can come in and complete this assignment as many times as I would like. And by complete, I mean submit it. So I'll talk about the submission button in just a minute, but we do not limit the number of times you can come in and try this assignment, as many times as you would like. Number of questions just tells you how many this particular assignment has. So this one has 3. It can have anywhere from 1 to 10 questions depending on the section and what's available there. Grading policy. Best score means that, whichever attempt is your best one is the one you get to keep, and partial credit is enabled. So if you answer 1 of 3 questions, you get credit for the 1 question. You don't get credit for partials within a question. So if you only answer half of the question, you don't get credit for that. You have to answer the entire question. So please remember, once you start the homework, you must finish it before you can work on anything else. So this simply means when I click start here, that before I do anything, when I'm leaving this screen, what I want to make sure I'm doing is down here in the bottom right corner, there should be a submit assignment button for students. You don't see it on my screen. This is the teacher preview, so I don't get to submit the assignment, but you do. So whenever you're ready to leave the screen, even if you've only done 1 of 3 problems, you click submit assignment. Number 1 puts it in the gradebook. Number 2 shows your teacher what you have been working on. And number 3, it won't lock you out of every other assignment. If you just leave the screen by simply closing the window, the system is going to assume that you're still working on that attempt. It's actually not going to close it out for you. So it's going to have you come back to this assignment, and it won't let you work on anything else. Tests, quizzes, topics, it won't let you do anything. So always, always, always click that submit assignment button. Over here on the side, we have these 3 general tools, and this time we actually have a 4th one, which is the calculator. So sometimes that's there, sometimes it's not. And sometimes it's a graphing calculator, and sometimes it's just a scientific calculator. Kind of depends on what the problem is calling for. For explanation, this one, you lose your question attempt because it's literally going to explain this problem. It's going to give you the solution and the answers. So it's not going to give you that and then say, okay, go ahead and type in the answers now. It's going to give you, an X on this one. You're going to have to come in another attempt to try it again. Really cool feature because sometimes you might just be stuck on this problem, not the entire problem type, because sometimes they look just different enough that we can't quite figure out what to do. Example, that just gives us a general example of what it is we're doing, and it will be a general example specific to this problem. It's not going to be just, any example. It's going to be very specific to the problem you're working on as far as the type. So different numbers, different scenarios maybe if it's a word problem, but the same type of question. So once you read through and you say, oh, okay, I totally understand what they want me to do here, I'm good to go, you can close that. You can click on example again to get another example, and then you can also message your teacher here. So this will open up a message center with the problem attached, and then you can type a message to your teacher so that, hey, we know exactly where to come and help you. All right, let's go ahead and get started here. So the table and scatter plot show the time spent texting, X, so they're telling us that's the X value down here, time spent texting, and the time spent exercising. And we did one like this in the last section, I believe, where they were correlating texting and exercising time. And if we think about one versus the other before we even get into the numbers here, if I'm spending all my time texting, like 6 to 7, 8 hours a day texting, I don't really have the time to exercise. So it's kind of makes sense. If you're doing more of one, you're going to be doing less of the other because you're taking up that time. So it's just kind of a correlation between the time spent on both of them. And this is 9 students. So we can see there's 9 spots here. That's what the dots mean. Remember, a scatter plot is in somewhat of a linear pattern, but it's not going to be a straight line anymore because we're looking at kind of real world information. And that doesn't always happen in a linear fashion. A lot of the time it happens more in like a scatter plot type idea, where we have them a little bit all over the place. Now, if they're in still somewhat of a line like this one, it's still kind of going down in a linear pattern, then we can draw a line of best fit. And they give us this equation of the line of best fit. So they drew the line and created the equation for us. very nice of them. They might have us do this on our own on one of these problems as well. So the line of best fit is a prediction line, so that I can plug in, if I say, if I spend 8 hours texting, how much, what do I predict the amount of exercising would be, which is Y. So it's a prediction line. It's not the actual line. The actual data are the X's. Those are the things that actually happened. But we can use the line of best fit to make a prediction based on what's already happened. So it's just a way to use information to plan for the future, kind of an idea. Or just to understand information too. Okay, so we have this table. It shows us, the 9 students and all their information. So 2 hours texting, they spent 6 hours and 54 hundredths, like hours, 54 hours exercising. And then we can, go down the chart here and see. So these 2 spent the same amount of time texting, but one exercised a lot longer than the other. So it's not a direct correlation or a direct relationship there. There's a somewhat of a relationship here because we have the same hours texting but different hours exercising. So that's individuality, right? That depends on the person sometimes. Okay, so we're going to use this information to fill out this chart below. And what it wants us to do is think about what was actually observed, what happened, what we would predict to happen using the line of best fit, and then the residual is the amount left over between the 2. So for this one, if we have 4 hours texting, we want to say what was the actual observed. So this one, we could look on the chart here, but sometimes that's going to cause us to estimate a little bit. We could go right over here to this table and say 4 hours, that was 4.5, right? That's what actually happened at 4 hours. And then for 6 hours, there's only one of them here, so that's 5.5. So those are my actual observed times exercising. Now what we're going to do is we're going to predict. So we're going to use this equation, y equals negative 0.4x plus 6.88. And that was a weird 8, okay? So now we're going to predict. So for 4 hours texting, I want to know what would my prediction be for the amount of exercising this person should do. Y equals, okay, so let's go over here to our calculator and we have negative 0.4, almost made that a very different problem, times 4. So this is the decrease, how much my time exercising is going to go down because of all my texting that I'm doing. So it's going to go down 1.6 hours from 6.88. So this is actually, because this is y equals mx plus b, this is a slope-intercept form of a line. This is the starting point for exercising. So they're saying this is kind of the cap for these students as far as what we think they're going to do. Okay, so that's going to equal 5.28. So 5.28. So this person exercised less than we thought they would based on this information. And what I want to do is take this and go minus 4.5 equals 0.78. Oops, 78. I actually want to make sure really quick that I'm not subtracting those backwards. It might be negative on that one. Observed minus predicted. Yep, okay. So I should have done observed minus predicted, which would have given me a negative. So I just want to make sure. So the residual is negative 0.78. So that's what the amount of hours they didn't exercise that we thought they would. All right, so for the next one, we're going to do the same thing. We're going to go y equals negative 0.4, but instead of 4.5, we're going to go with, sorry, not 4.5, 6 instead of 4. So we're going to predict the amount of time we think they should have exercised based on this. So let's go back to our calculator, and we have negative 0.4. Oops, still had other stuff in there. Negative 0.4 times 6. So we're going to take 2.4 hours away from the kind of cap there. Plus 6.88. Why is it not working? All right, so y equals 4.48. So 4.48. So they exercised more than we thought they would. Right? We only thought they'd go about 4.5 hours. They went 5.5 hours. So these are above and below where we think they would be. So I'm going to go to the beginning here and go 5.5 because it's the observed minus the actual minus the predicted. So they exercise for 1.02 hours more than we thought they would. All right. So if we're looking at these, so shown below are the 3 scatter plots and their lines of best fit. Also shown are their 3 residual plots. So residual, remember, that's the time left over, meaning that how close is the line of best fit to the actual information. So if we have scatter plot A, all of these dots are on the line, right? So there shouldn't really be any residual because the line of best fit is going through all of those points. So if I choose one of those points for X, it should be the exact point on that line. There shouldn't be anything left over there. So the residual should honestly be 0 for all of those. There shouldn't be anything left over. If I'm looking at scatter plot B, this line and then this data doesn't really fit much at all. It just went through the center of it. But this is really not a very good line for this data because this is a bit more of a quadratic information type idea. So the residual is probably going to be pretty far off of this line because if I'm looking at, say, 6 here for X, if I plug in 6, well, I'm going to get somewhere up here around 4.5. I'm definitely not going to get down here at the closer to the 2 mark where it actually is. So the residuals are going to be pretty far off on this one. And then plot C, we can see it's pretty linear, but the line isn't perfect. They're a little bit off the line. So the residual may be a little bit above and below, just like we see it here. So the residual plot will actually match pretty closely to what it looks like on the actual scatter plot. So if we look at the residual, so we can see this same U pattern, which makes sense for this guy because the residual will be pretty far off from this line because all the data is pretty far away from that line. So this one would definitely match scatter plot B. And then this guy, they're all in a nice straight line and it's on 0, it's on X, right? So the residual, what's left over would be 0. There really shouldn't be anything left over if all of the data is on the line. That's a linear function. So this is going to be scatter plot A. And then this one, just like this guy where it's a little bit above, a little bit below, it's the same idea with the residual because if I calculate, say, the residual for this point, my data would be up here, which is just a little bit off. So the residual would be actually a little higher. So it's flip-flopped from what kind of what you might think, but it should match pretty closely. In fact, the dots actually match pretty darn closely. They're just on the x-axis now instead of kind of going off on the graph diagonally like they are here. So this is plot C. Oops, not B, C. All right, so now let's kind of describe them. So what best describes the line of best fit for this scatter plot? So with this one, a perfect model means that they are on the line, they are perfectly aligned with the line of best fit. That's definitely not this one. A good but not perfect model means that they're all pretty close to the line. They're not all on it, but they're pretty close. Not appropriate means that they're barely anything is even near the line. It's all kind of scattered and like a cloud, which this isn't really a cloud, but it's definitely, there's nothing near the line except for maybe a couple points here. The rest of them are pretty far away. So that's not appropriate. If we're looking at the residual plot 2, which matches plot A for scatter plot, well, those ones are right on the line. That seems like a very perfect model, especially since all the residuals are 0, meaning that our predictions are exactly what's actually happening. That means that is a perfect model. And for this guy, they're all pretty darn close, but they're not on the line. There's a little bit of residual there above and below, so that means it's good. It might not be perfect, but it's good. And generally what we're looking for is a good model. We We aren't always looking for a perfect model because it's not possible if we don't have them in a nice straight line like this. All right. So let's do our last one here. Shown below are the scatter plots for 4 different data sets. Answer the questions that follow. The same response may be correct for maybe the correct answer for more than one question. So we have 4 data or scatter plots here. We can see this one's a little spread out, but it's still pretty linear. I can kind of draw a line between them. This one, definitely closer together, but it's going to be a negative relationship. Then we have closer together, but a positive relationship. This guy has really no relationship at all. It's just kind of a cloud of points, right? They're just all over the place. So now that we've kind of looked at it, we've thought about our data, let's go ahead and look at the questions. So for which data set is the correlation coefficient R closest to 1? So if we've never heard this before, this would be a really good time to click on an example so that we know what is it talking about right now. Because if we've never heard about the correlation coefficient, then we wouldn't really know how to answer this. So the correlation coefficient measures the linear relationship between 2 values. The value of R, which is our correlation coefficient, is the number from -1 to 100. And we can directly think of this as a percentage. So -1 is -100%. 1 is 100%. And what we can think of on this is -100% means that it's negative relationship. So this is a negative relationship. And it's they're on the line. So if I'm saying it's a -1 correlation, it is a straight line going down, and all of my points are on this line. So they're all on the line of a negative slope. 100% positive means a positive relationship, and on, I don't know why I put 1 on the line, on the line again. But this time it's going to be going upward, and they are all on the line. So this is a 100%. I put that one next to the line, on the line, right on the line, right there. So all of my data points are on the line. If it's 100%, that means it's on the line. So we're either going to be 100% negative slope, 100% positive slope, or somewhere in between. So 0 means no correlation at all. Correlation. Sorry, I want to make sure I was spelling that correctly. I was thinking about it too much. So no correlation at all, because that's a 0% if we think of percentages. So that means nothing is even anywhere near a line that I could possibly graph. So the closer we are to each other, the closer we're going to be to either 1 or -1. The farther apart all the data points are, the closer we're going to be to 0. And if there's absolutely no pattern at all, it's just a big cloud of dots or data points, then that's a 0 correlation. So this is just the idea here, and they tell us this, you know, X increases as Y decreases. So this is a negative linear relationship. The slope is going down from left to right. So it's not going to be a -100% though, because I can't draw a line that grabs all these points, but it'll be somewhere near -1. It'll be closer to that -1 than the 0, because there is a linear relationship there. This guy has no linear relationship at all. It's just a cloud. So this would definitely be a 0. But this one, as X increases, so does Y. There's a positive increase there going from left to right. So this one's going to be closer to +1. So this is the idea as we go through here. So for which data set is the correlation coefficient R closest to 0? Well, I'm looking for this cloud here, right? So if I scroll down, it's going to say figure 1, because that's the cloud. That guy doesn't have any correlation, any relationship to each other. Which data set includes the strongest positive linear relationship? So strongest positive means they need to be going up from left to right, and we want to find the ones that are closest to each other. There's only one here that's positive, so it's pretty easy to grab. That's going to be figure 3. And then the last one, for which data set is the correlation coefficient closest to -1. So we do have two negatives here. This guy, figure 2, is going down, and figure 4 is also going down. So we want the closest, which is why they grab figure 2, because these data points are closer together, like if I drew a line in between them, than these ones. So let's go ahead and try this last one out here. So we get 2 examples on this one, because I'll do this problem too. So for which data set is the correlation coefficient R closest to 1? So that's +1. I want a positive relationship. So I'm going to focus on figure 1 and figure 3. Figure 2 is negative. And figure 4 is just kind of blah, it's everywhere. But 1 and 3 have a positive. They're going up from left to right. And we want the one that's closest to R, right? So the data set correlation coefficient R closest to 1. Well, that means 100%. This guy is definitely closer together than these guys. They're a little bit more spread out. So I'm going to pick figure 3 because that's closer together. Which data set includes the strongest negative linear relationship between its 2 variables? Well, we only have one negative here. This is the only one that's showing a negative relationship. So pretty easy to grab this one as far as it's going to be figure 2. If there were more than one, we're just looking for, when it says strongest, that means which ones are closer together, right? That's they're going to be closer to that 100% or -100% mark. For which data set is the correlation coefficient R closest to 0? Okay, we're looking for the cloud, the kind of blah one, so that's going to be figure 4. All right, so that was section 6. I believe that is the end of chapter 4, so I will see you in chapter 5.